So today we're going to be learning a cubic identity. So this this is our cubic identity for today. So it says that for any reals a, b, and c, a cubed plus b cubed plus c cubed minus 3 times a times b times c is equal to a plus b plus c times a squared plus b squared plus c squared minus a times b minus bc minus ac. So this equation looks pretty interesting because it includes the sum of a and b and c, and it includes the sum of the squares of a, b, and c, and also includes the sum of the cubes of a, b, and c, as well as the product of every two of the three numbers a, b, and c, and the product of all three numbers a, b, c. So this equation looks pretty interesting, and as we do our problems together, we're gonna further realize that this equation is actually really useful in solving algebra. So, but before we start, we can look at some techniques that we can use with this identity. So firstly, what happens if a plus b plus c is equal to 0? If a plus b plus c is equal to 0, then this entire thing will be equal to 0 because 0 times that will just make everything 0, which means that a cubed plus b cubed plus c cubed minus 3 times a times b times c will be equal to 0, which gives that a cubed plus b cubed plus c cubed is equal to 3 times a times b times c. So that's pretty useful. And another technique is that, I'll just write that again. Number 2, for this expression here, a squared plus b squared plus c squared minus ab minus bc minus ac, this, if we factor this, we get half of a minus b squared plus b minus c squared plus c minus a squared. And if you expand this, you'll realize that it becomes this expression. So this is pretty useful because later on you'll see that because the smallest value of the square of a real number is 0. So this will actually be pretty useful for, we'll realize that, we'll find that out as we do our problems. So these are the two things we must keep in mind as we do the problems. And yeah, so that is the cubic identity we will be looking at today. So I'll just draw a line here to separate this from our problem again. I'll just draw that again. Wait. Oh, sorry. There you go. Okay. So our first problem is that it's to factorize. I'll put that in blue actually, to separate it from our solution. So we want to factorize. We want to factorize a minus b cubed plus b minus c cubed plus c minus a cubed, where a, b, and c are reals. Okay, so we can already see that we can kind of use this equation because it's sum of the cubes of three numbers, three reals. So yeah, why not we just put each of these numbers as some variables to make things easier. So let's say that x is equal to a minus b, and y is equal to b minus c, and z is equal to c minus a. Well then, so basically we want to factorize. We want to try find an expression for x cubed plus y cubed plus z cubed. Okay. But looking at this, we can easily see that x plus y plus z is equal to, and if we just add all these expressions together, all the variables a, b, and c cancel out and leave us with 0. So we get that x plus y plus z is equal to 0. And looking at this identity, we see that if x plus y plus z is equal to 0, then x cubed plus y cubed plus z cubed will be equal to 3 times xyz, which is pretty useful here because we're trying to look for an expression for this. So we get that x cubed plus y cubed plus z cubed is equal to 3 times xyz. And we can just plug these expressions back into xyz to get that this expression can be factored into 3 times a minus b times b minus c times, b minus c times c minus a. And there is our factored form. Yeah, so here we use one of our techniques here to prove this statement, to factorize this expression. Oh yeah, and in this video, we're going to be focusing more on, we're actually going to focus more on this technique. And then in the next video, we'll focus on the second technique, because these two techniques are really useful, and I want to kind of focus on each of them more so that we can look more in depth into them. So yeah, we're just going to focus more on this one today. And in the next video, we're going to look at this. So yeah, that's how you do this problem using this identity. So let's erase this to do the next problem. Okay. So the next problem is, I'll write this in blue again. Second problem. If we have three real numbers, a, b, and c, and a plus b plus c is equal to 0, and a cubed plus b cubed plus c cubed is equal to 0, then find the value of a to the 2009 plus b to the 2009 plus c to the 2009. Okay, so here, again, we can use this identity. We see that a plus b plus c is equal to 0, which means that straight away, because we have this identity in our mind, we can straight away deduce that a cubed plus b cubed plus c cubed is equal to 3abc. But then we also see that a cubed plus b cubed plus c cubed is equal to 0. So actually, using these two pieces of information, we find that this is that 3 times a times b times c is equal to 0. I need to write that in black. 3 times a times b times c is equal to 0. And so from these two information and using this identity, we easily found a very important piece of information that will help us with finding this. And now from here, we just have to do some problem solving and we'll easily find this. So here we just get that a times b times c is equal to 0. And so at least one of a, b, and c must be equal to 0 for this to happen. So let's just say that a is equal to 0. Let's say that a is equal to 0. And from here, we know that a plus b plus c is equal to 0. So if a is equal to 0, then b is equal to negative c. And c is just equal to c. So if we plug these values into here, then we get that 0 to the 2009, which is just 0, plus negative c to the 2009. And c to the 2009 is just c to the 2009. And since 2009 is an odd number, we can just take this negative 1 out. This will just be equal to negative c to the 2009 plus c to the 2009. And that just cancels out and gives us 0. So the answer to this is basically just 0. So this looks pretty complicated, and it looked like we had to kind of factor this or something, but no. We just used this identity to find a statement that kind of gave us a pathway to simplify this expression and find an easy way to find the value of this. So yeah, this identity has turned out to be kind of really useful to use in these kind of scenarios. Yeah, so now that we solved this problem, we can move on to the next one, which will be a bit harder. Oh, I've just erased the line. Okay, so the next problem is that given that x, y, z are distinct integers, so x, y, z are integers, but they're distinct. I'll just write all these down because it'll be helpful. If they're distinct integers, oh, sorry about that. If they're distinct integers, then, and we have the information that x plus y plus z is equal to 0, and x cubed plus y cubed plus z cubed is equal to negative 36, then find the number of triples of solutions. The number of triples of solutions x, y, z. Yeah, and unordered triples of solutions. Yeah. So how would we do this? So again, we see that again with the problem before and the problem before that, we see that we can this identity jumps into our mind as soon as we see that we see that sum of some integers is equal to 0, and then we're given, like, we're told to find or are given the value of the sum of the cubes of those numbers. Then we can instantly use this to do something with this, to solve the problem. So here again, we can use this identity to solve this problem again. So here we know that x plus y plus z is equal to 0. So then again, x cubed plus y cubed plus z cubed will be equal to 3 times x, y, z. So, and which gives that 3xyz will be equal to negative 36. And this gives that x times y times z is equal to negative 12. So we know that x, y, z are distinct integers. And we know that, okay, I'm going to put this in red. So we have to consider that x, y, z are integers, and they're distinct, and their sum is equal to 0, and their product is equal to negative 12. And since x, y, z are integers and they're distinct, it's actually pretty easy to find the triples of all the triples of solutions of x, y, z that satisfy these conditions. So because we just have to find like the factors of 12 because x, y, z are integers. So if we do this, but then x times y times z is equal to a negative number. So either all of x, y, z have to be negative integers, or one of them have to be negative. But we realize that not all of them can be negative because that's not going to satisfy this statement. So this means that exactly one of them have to be negative and the other two have to be positive. So if we just kind of YOLO all the solutions using these informations, then we see that the only ones that work is 1, 3, negative 4, and negative 4, 1, 3, and 1, negative 4, and 3, and 3, 1, and negative 4, and 3, and negative 4, and 1, and negative 4, and 3, and 1. So that's a total of 6 solutions. So our answer is 6. So yeah, that's basically how we use the cubic identity to solve these kind of problems here. So the problems we did, they looked pretty kind of, yeah, it was kind of this identity. The reason I really like this identity is that it can kind of be used in a really unexpected way, because this expression looks really, really complicated in general, but then you can deduce some really simple statements that become really useful later on when you solve problems. So yeah, using so here in this video we focus on using this statement to solve these kind of problems. But in the next video we're gonna be focusing more on this. Well, we're gonna be looking at this also at the same time, because this is a really, really useful fact using this identity. But we're gonna in the next video we're gonna start looking at this statement too. And why not, you guys? Why not try actually? No, I don't have the problems yet. So yeah. So hope you enjoyed this video and learned how this cubic identity can be useful to solve algebra problems. And yeah, see you in the next video about this cubic identity.